So it seems like we can start. My name is Kanchan, and the talk is going to be on data placement in Linux. This can be divided into two blocks. One is what is data placement and what is happening in Linux to support this. Let me start with the question, how many of you are having a laptop with SSD? All right. And if I use the words like NAND block, NAND pages, erase block, garbage collection, write amplification, do these terms ring a bell? Do these terms ring a bell in terms of SSD, or is it something that perfect? Okay. Okay. So it looks like I'm gonna bore you a bit with respect to like all this stuff, and that is going to I think set the context with respect to what do I mean by data placement and why it may be relevant if you are using SSD. So this is crucial for improved I/O performance, usable space, and endurance. Now these are the buzzwords. I think I'm going to explain these. But important thing to highlight here is that the logical placement that we typically do when we are having the SSD, we will be using it. We would be using it in like various ways. And when we are using it, we are basically doing logical placement. And the physical placement that is happening at the device level, that may be completely different. And who decides how exactly the data is placed? If you look at this simple sequence, so we may be having a data creator. That could be any application that you have, and then you would be having maybe a series of system softwares, maybe layered. You can think that if this is a kernel, it could be the VFS, the file system, block layer, maybe RAID, MD RAID, and stuff. And then you would be having some driver, and eventually you will be having the storage device. Now, in this series of things, anyone can do some transforms, and layout may change, right? But so everyone may have this, this sense of control that yes, I'm writing the data, so maybe I'm deciding where the data goes, right? But all this is actually illusion. The component that is closest to the SSD that has the final say, and that typically runs inside the SSD. So if you see the picture over here, it's a complex picture maybe. But this shows a very simple diagram of how SSD is architected. And what it actually shows here is 8 NAND chips. The data is going to get stored into those. And these chips have been organized in a particular way. What you see here is like multiple channels, and there's a controller. This controller is like similar to how we. So this can be seen just like a regular computer. We have got a CPU. These are multiple pathways into NAND chips. Data is going to finally land into those, and what you see over here is a structure called super block, and this particular super block has been created by the SSD so that things become fast. What the hell? I'm really sorry. No, I didn't mean that. I'm still here. Yeah. So the super block is important in the sense that this is where your data is going to land. But so what I've done here is that I've created a super block in this, which is going to span across multiple chips. If you deal with RAID, you can just think that there is a RAID inside the SSD that is trying to increase the parallelism within the device so that things become fast. But it may vary how large this particular super block can be or should be. It may vary from SSD to SSD. This I think should give some glimpse, but there are more details. 3 points to make. The first one, SSD is going to do out of place writes. So it has its own page level mapping, and when I say page here, this is a SSD page, not our system page, 4 KB or huge pages and stuff. This is something that SSD decides. As far as host is concerned, yes, host typically is going to write in units of 4 KB. If we are at the lowest level, if you are above the file system level, yes, you deal in terms of bytes. There would be a table within the SSD, and that table is going to do a mapping between the host issued logical block addresses and the logical block addresses that SSD actually is going to decide, and that's actually called physical page addresses here, PPA. So that's the mapping, and data is getting written into those NAND pages here. Each page is the smallest unit that SSD can write, and multiple pages are organized into a block, and once you write a page, you cannot overwrite it. You cannot do in place writes. That's how things are physically. It's about physics. It's you just can't. You will have to do something called erase, and only then you could like rewrite it. Now what is happening over here is that if I do one more write, SSD will basically place the data into a new place, just like file system do. And in like some file systems, right? Not ext4, but let's say if you use ButterFS, you know that it does copy on write, right? So this is like something like that. So it is going to write the data in a new location. It is going to invalidate the previous mapping. In a way, now what you have is that you have got a hole which is no longer valid, but yes, it's there. That's the first point. The second point is what I mentioned in the previous slide is that the SSD would be having a abstraction called superblock. It is going to combine many multiple blocks so that it can write things parallelly. So in this case, a block has been created across multiple NAND dies, similar to RAID, primarily because we want high throughput automatically. And the last one here is a crucial point. So for a particular superblock, we would be having a single appoint point. And generally, for the entire SSD, we would be having a single appoint point. This actually means that whatever you place, regardless of how you are placing it, is going to land into a single erase block. You can think just like this is like a pointer. It's going to move in a log structured fashion. Once a block is full, it will change the block, and it will write in a sequential fashion in that particular block. So this single append point also has some implications. So yeah, these 3 points, and this is how things are internally within the SSD as far as physical placement is concerned. But now, why all this, right? Like, this is all about SSD, right? But the moment we come out of it, we come into Linux world. We are, let's say, file system guys, or maybe we are database people. So in case of file system, we know that the file system, we start by doing MKFS. So we do format, and the format varies. XFS would have its own on-disk layout. ext4 would have its own. So in case of XFS, we have something called allocation group, which are like sequentially placed, basically. Similarly, ext4. And in a way, this is like starting of the logical address space, I would say. So you see this figure here. Imagine XTB of device or SSD here, and XFS is going to be creating, this is a bit simplified, but yes, XFS is going to be creating multiple AGs, and in the linear address space, that's how it will look like. But, and it's like this, right? That if you are creating, that XFS is designed for scalability, and the AGs are one of a way to do that. So sometime, because you have been using XFS, so you would probably create, let's say, 2 directories, because you know that those 2 directories would be placed into 2 different AGs. So imagine you wrote data X into AG0, and you wrote data Y into a different directory, and that would be placed by XFS into a different AG. So in a way, you get this illusion or you get this impression that yes, this is what has happened, right? That logically things are placed into two different AGs. But what might be happening internally is that within the SSD, I have shown 4 super blocks over here. Both the data X and data Y would end up going into the single super block here. Whatever is the append point here, wherever it is, it's going to be data X and data Y would be placed there. So this is not just about file system, it could be about anything, right? You may not be using file system, you may be having your own application maybe. Some databases do try to skip file systems, and in that case, you might be writing things into file, you might be categorizing them into groups and all that, thinking that yes, logically things are separate and all that, but you may just be hitting the same super block all the time. But while that is happening, what would be the consequence of it? What is the harm if it is happening, if it is going into the single super block? And to actually to talk about it, I think I will repeat that in case of SSD, we cannot just do overwrites, we have to do write. And if you want to do rewrite, you will have to do a operation called erase. And erase unit is much larger. I think the same thing, right? The big super block which I showed you. But if I need to erase that particular big super block, I can only erase once I have moved all the valid data, because we can't really lose the data, right? The data is important. And this process of moving the valid data from one particular super block or one particular erase block to another one is called garbage collection. As you know, moving means we will have to read the block and we'll have to write it somewhere else. Now, this is something that would happen inside the SSD. And this is something you never really asked. I mean, this was hidden to you, right? I mean, you would do some writes or you would do some reads. Those are the writes and read that you asked. Nothing extra in that. Whatever is happening in the garbage collection, that's all extra. You never want that, actually. To actually show this problem, there is this thing called write amplification factor. So this is just that this is a ratio of the writes which actually happen to the SSD divided by the writes that you ask SSD to do. In the ideal case, everything would be, like both the things would be same and you will get a value 1. And if 1 is there, that's awesome. Nothing to improve, everything is perfect, right? But that may not be the case. And if it doesn't happen, imagine the WOF is 2. What it actually means is that if WOF is 2, this actually means that your SSD lifespan would be reduced by half. If your SSD was supposed to die in 5 years, it's going to die in 2.5 years. And SSDs are meant to die. Or rather, what happens is that all those erase blocks, whatever I showed you in this picture, right? So the lifespan of these erase blocks is based on how many erases can be done on this. So this is called program erase cycle. You write, you erase, you write and erase, and after n number of write and erase, that particular block is going to go bad. So there's a fixed life that is there with SSD, and that actually depends on how many times you write and how many times you erase. If you write more, you will basically finish your 5 years fast. If 5 years is the guarantee that you got when you actually bought the SSD. The other part here is so that's the point. That's the implication about endurance and the total cost of ownership. The second part is the performance, which I said that whatever is happening due to GC is extra. You never ask for it, and if it is happening while your IOs are also happening, it's basically interference, right? You don't want it. You don't want your IO to be slowed, or you don't want SSD bandwidth to be shared by internal operation. And this problem, this high write amplification problem, is more likely to happen when we end up mixing data of different lifetimes into a particular super block. And in this one, what I'm trying to show here is that imagine that so H means hot and C means cold. Imagine that you have two types of data. One is hot. When I say hot, it's going to be more likely to be like updated. Cold is something you write once and it's gonna be, valid throughout. Imagine some files are getting written more often and some files are more likely to be, it's only read. They are probably not likely to be modified, right? So let's classify these two. And if you see the sequence, what is happening here is that H1, C1, S2, C2, this actually means that there is one hot write, then one cold write, and then another hot write. In the sequence, if you see the left-hand side, there are two erase blocks. Each erase block has 4 pages. When I'm writing H1, it gets placed over there. C1 gets placed into the next page within that particular block. Similarly, the whole block gets written. Then next 4 gets written into the second block. Everything is fine. Now you end up modifying your hot data. So imagine you end up writing that particular file which was hot, and you write H1 dash, S2 dash, S3 dash, and H4 dash. What happens now is that within the SSD, it will be creating, because it cannot do in-place writes, it will have to do out-of-place writes. It's going to be allocating a new block. It will write all that thing, and the previous data would be marked invalid. So H1, S2, S3, and H4, they have been marked invalid. So this is the current scheme of things. Now what we have over here is that there are 3 blocks. 2 are partially full, and the last one is full, like completely valid, I would say. But in these 2, there is some valid data and some invalid data. And imagine that if SSD has to do garbage collection, this actually means that SSD has to produce a single free block. Then in that case, it has to move the valid data, which is C1, C2, C3, and C4 somewhere else. Now that is what is going to create extra reads, because you will have to read them within the SSD, and then you will have to write also. So you will do those 2 things. Can we do anything to improve it? The important point here was that there is a copy required to reclaim or to basically produce a free block, and the copy is C1, C2, C3, and C4. In the right hand side, what you see is the same sequence, but what you do this time is that you see this thing called stream X, stream Y. You say that with your writes, you decide to provide a hint. You say that all the H1, S2, S3, and H4. With that, you specify a tag. You can think it's just an integer value. And you say that they all belong to one stream called stream X. And all my cold writes belong to another stream, and they could be called, let's say, stream Y. Again, 2 numbers, 0, 1, 1, 2, whatever. If you do that, now this is a different SSD. This particular SSD understands these streams, and it will basically place H1 and all the hot data and all the cold data separately. What is happening here is that it is writing it into 2 different blocks. It is not writing into the single append point. So what is happening in the right hand side figure is that we have got 2 append points. Here we only got 1 append point. Everything was log structured. Here also it is log structured, but there are 2 append points, stream X and stream Y. With that, what happens is that when you overwrite, you end up invalidating your whole block. So all the H1s, it becomes invalid. Now, if the garbage collection happens, it can reclaim the entire thing without moving anything. It can just erase the whole block. So there is no extra read and there is no extra write. That actually means that in this case, the write amplification would actually be 1, while in this case, the write amplification would be more, because SSD is writing more than you asked for. And all this happened because the different lifetimes were intermixed into a particular superblock. So in general, we actually have a semantic gap between how file system thinks, or how application think that they are writing data to the device, and how device actually writes. And that particular gap can be reduced if we have got some extra knob or some way that SSD can tell us. There is no other way. We can't just imagine it. SSD has to tell us something, and if we use it, it may place things differently. I mean, in this case, SSD is in charge all the time, right? And flexible data placement, FDP, is a way to give some extra power to the host. In this case, let's say it could be your Linux box or it could be anything else, wherever you are putting your SSD. But this is about giving control to the host so that actually it can do the physical placement. It can decide where the data lands. And this has to be standardized, because if it varies across SSDs, this may not fly well, right? So for NVMe SSDs, this has been standardized already. And with that, what happens is that SSD is going to report multiple append points, not just one. And which of the append point to be used for this, you would need some kind of identifier, and this particular identifier is the placement identifier. So you earlier you were just sending the write, now you would send the write, but you would also send this placement identifier. And that will enable you to choose a different super block within the SSD. And in this case, the super block is called reclaim unit. This is the term that comes from the specification, but it means the same thing. So if you look at the right hand side picture, what would happen now is that the same thing, imagine XFS has two AGs, data X and data Y. Now with XFS, when the XFS actually writes data to the SSD, it has to send a placement identifier. If it does, it will actually go to a different super block. In this case, we have got multiple append points, 2 append points in this case. And for AG2, it can actually place it separately. So there is so the semantic gap that we have between the file system and the device, that can be reduced or that can be eliminated. This whole thing is backward compatible. When I say backward compatible, this actually means that there is no such rule that you actually have to write sequentially. You can actually write randomly, but you have to pass the same tag. If you want to group the data together, you say that the data tag is same. So, and imagine if you end up passing a wrong tag. Imagine that SSD said that I'm supporting 4 tags, 1, 2, 3, and 4. If you end up sending 5, SSD will still tolerate it. It will not give you error. It will just place it in a default stream, and that will be called like no tag stream basically. This has been done so that applications life still remains easy, and things can be incrementally improved. There's a feedback mechanism. You could know that the benefit is not coming. You will not get the errors, but when you check it, you may see that, oh, my WOF, my write amplification has not been improved, and that part is coming from the feedback mechanism that is there from the device. Device is going to provide extra log pages that you can query, and you would know how much data actually has been written by the SSD and how much data host asked to write. And you could, with these two values, you can again determine the write amplification. And there is an event called media reallocated event. This tells how much data has been moved by the SSD from a RU. This actually means that, imagine if you place the data in a particular RU, you don't expect that this data would be moved normally. But if it does move, because SSD did the garbage collection, so it will actually tell you that. And that could be the case because you may not be doing a very fine job with respect to segregation. And the whole model is backward compatible, so no one is actually forcing you to be super accurate with these tags. But the feedback mechanism allows you to improve incrementally over time. And if you want to know more about the specification or the device feature, there's a link over here. But I think maybe the more interesting part for the audience would be where we are in the kernel, what we are doing in the kernel for this. So I think the crux of the problem here is that what interfaces do we have in Linux that allows the application to send something extra, some kind of extra tag with the write. And we have got bunch of calls, system calls like write, write v2, but nothing really fits well. We do not have a way to pass the extra identifier to guide the placement. ioctl is one of the way, but that's synchronous in nature. So we need to think of other options like lib-io and IOU ring, because these devices happen to be fast and they are parallel. So you would really need asynchronous IO for it. And this is actually about sending writes, which is like fast path operation, unlike the ioctl, which happens like once in a while. So the first attempt to basically enable it was done via something called IO passthrough. So this is a facility that was merged in kernel 5.19. If you look at the right hand side figure, the green line, this is what IO passthrough is. It has two elements. The first one is a carrier device /dev ng0n1 that is created corresponding to the NVMe SSD, and this particular device can be used using IOU ring. And in order to do this, we ended up creating something called uring command within the IOU ring. I think this can be called asynchronous ioctl to simplify things. So this particular path was created for various other reasons, not actually for FDP, because we see the emergence of non-block IO, non-block semantics devices, basically like KV, key value, and the computational storage. But yes, I mean, this is like one part of it, that there are new devices are emerging and they need to be supported. They do not fall. They do not fit well into the block abstraction. So we need something for that. So this path was solving it. But beyond that, we are having this problem of that if we actually introduce a generic syscall for something, that need to be maintained permanently, and it has to have widespread appeal, which may or may not be there in the beginning at least. So the purpose here is that this whole thing allows new command to be passed without actually having to introduce generic syscalls. And the first one here, FDP write, is the one which is possible with this. And many other things are also possible, like many other commands are also possible. Like if you look at the last command, that's the kind of command which you like send to the device. You say that I want to write, but I'm not going to tell where I want to write. You decide where where you place it, but wherever you place it, return the LBA, and that's called like Joan append. And there are a bunch of other cases as well. I think I have I have already added a link for it. So maybe if you're interested, maybe you can take a look at it. But coming back to the placement, right? To do the placement, I think if we like double click on it, it basically looks like this. This is the command that a user space application can send using IOU ring. And here everything looks like very similar to how you send a write command. You will tell that the opcode is a write opcode, because you could send read as well, and you would specify a buffer to write. You will say that this is the buffer length, and then you will tell where exactly you want to write it. So this is going to be telling the location on the disk, CDW11 and CDW12. The new part is the placement ID. So the placement ID is something that you would populate over here, and if you keep the placement ID same, your writes will basically land on the underlying superblock, or in this case it's called reclaim unit. Now this is something that has been deployed into CacheLib, which is Meta's caching engine, which has been deployed, which has been open source already. And in this case, this is there are two I/O engines with different I/O patterns. So there is a block cache and there is a big hash. The block cache is having large objects with the cold data. Big hash is having small objects with the hot data. And this was getting intermixed. And this, when this is separated on the FDP SSD, the kind of gain that you see here is that all the right hand, all the red curves are they are showing the WAF, high WAF basically. So high WAF is bad, low WAF is good. When the device is 50% utilized, it's like 1.3 or 4. It goes up to 2.5, and then it goes up to, when it's 100% devices utilized, it goes above 3 point something. But on FDP device, it still remains at 1. The same happens to the performance. This is the P99 latency, and I think people can take a look at this talk for details. But this is all about pass-through. Now, what about block I/O, right? So, block I/O is something that has been included very recently, last month. So, in the 6.16 kernel, the in-kernel interface is that we introduce something called max write stream at the block layer, and NVMe driver is going to populate that with the number of placement IDs it has. And if you do that, you will be able to see, you can like query this cat sysblog NVMe 0 q max write stream, and it will tell you how many streams are actually there. And what about application, right? How application can start using it? So there are two ways. The first one is that using the existing per file or inode live hints. So this is something that is already there in the kernel FCNTLs. On a file, you can specify one of those hints, and you can either set them, and then you can also query it. So these are used over here. They are mapped to the FDP placement IDs. This allows overall 6 segregation level, because we have this count 6, which may or may not be ideal. That depends on the underlying device. If you have a device which actually has more, likely you will have more. So this may not go well. You need something better than that. And also because for the whole block device we have a single inode, so if you are having multiple applications using the same inode, again you may get into troubles. So we also added something called per IO stream interface in iUring, and that is something which that figure is for. So application is going to send a SQE. In the SQE there is a new field now. It's called write stream. You can put you can put a value over there, and that value could be much larger actually. That value could be 0 to 255. So you could actually specify 256 levels. So segregation is the possibility of segregation is much more in this interface, and that's it. I mean, you just specify the write stream, and the remaining things you were anyway doing before as well, nothing new. And what happens is that the kernel infra takes care of propagating this write stream to, let's say, KIOCB and BIO and NVMe. At NVMe it becomes like FDP. Otherwise, for the rest of the kernel, it's all a new entity called write stream. If you want to look at the patches, take a look. So this is cemented. While this is cemented, this particular part is not. So this is about file I/O. The file I/O is like in this case, I think things get a bit more tricky because we have applications and we have file system. So application might have its own policy about how the file need to be placed, but at the same time file system has its own policy, right? So I think we have both the camps. One is application-driven hints folks, and we have file system-driven folks. So, but as far as SSD is concerned, it has got no idea. As long as pass tags are honored, the data would be grouped as originally intended. But what need to be ensured is that the kernel and application shouldn't collide. This actually, by this I mean is that if the application is passing some hint and the file system is also passing the same, then it may not be desired maybe, or it may collide, right? I mean, so that part need to be seen, that both are working together. And some file system may want to leverage the placement for the file system metadata or the file system journal maybe. Even if it is supporting the application-driven placement, we can think that it probably is the business logic of the application to decide where its data should be. But as far as metadata is concerned, that's a file system own thing, right? And application knows nothing about it. Only file system can actually do the placement for that. And the last thing here is that the stream is a dynamic entity, unlike those hints. So those hints were fixed, while stream would actually vary depending on the device. So you may be having 0 streams, you may be having n number of streams, you don't know it, right? So you need to query how many are available. So this was a bit simple because it's fixed, those live hints, but these are not. So the current patch set which is under discussion is, it basically exposes three new FCNTLs. The first one is to query the number of streams that actually are available to the application. Application need to query this from the file system. It may be 0, it may be non-zero, but yes, once it gets the number, it is sure that yeah, it can use it. But the file system decides how many streams it want to expose, and if this number is non-zero, then application can set the stream on a file. And if you want to know, it can query it using this ioctl. And as far as collision is concerned, so that is being handled by a new callback in the super operation. The file system can decide to implement this particular callback. If it does, it can decide to reserve some for itself, and remaining it can be exposed to the application. So this actually helps to avoid the per file system plumbing, particularly for the file system which do not have any special policy, because we have a fallback over here. If this particular callback is not implemented, we just use whatever is there on the block device. So if block device is showing 5 streams or 8 streams, they all will be shown to the application. So only the file system who have a special policy, they need to implement this callback and do something special. Otherwise, everything gets exposed to the application. But this is still under discussion, so evolving. So we need to see how this turns out to be. But the summary here is that the data placement has implications. At this point, we have 3 I/O paths. 2 are already cemented in the kernel. The first one is I/O during pass-through. This is mature because it's been around since 5.19. The block I/O path is something that got landed recently, and it also includes per I/O stream. The file I/O is ongoing, and as far as tooling is concerned, it's there. Almost all the tools are actually aware of FDP or the placement. But yes, I think if the file I/O patches get merged, when they get merged, in what form, based on that, things may change. And we have got a couple of real-world applications that are making use of it. And that's it. I think now I'm, this is now the right time to say thanks for listening. And if you have questions, I'm happy to answer. It has both options, and I think this one is using the block I/O. Yeah.
Yeah. So how many displacement streams do you get now, and
So the kind of number that you saw over there in this particular device had 8 streams. But things will actually vary depending on the vendors. So that just happened to be one SSD. And in this case, actually what was required was only 2, right? Because here, 2 is enough to get this kind of benefit. So, so yes, it really depends on, it varies from device to device. And I think one size may not fit all. And it has some cost, actually. I mean, when you increase the number of streams, you actually have to have more internal resources within the device as well. Device does some amount of buffering for each stream. So it's similar to the page case that we have in Linux, that you don't just try to write everything to the NAND the moment it comes. You try to gather the data and then you write it, right? Now, if you have a single append point, you basically gather that much, right? But if you are having multiple write points or multiple append point, you would need to have a bit more RAM. So so yeah, but you know, I think that's something which is a device specific detail. Yeah, does that answer your question? Okay. Yeah.
As far as I know, there is another technology called the zone
Yeah.
SD, which allow the system to give hints on where to place the block. Do you know which is the main difference, if any, and which fits best in which situation? And yeah.
No, you're absolutely right that the GNS was also introduced to solve the same problem. And actually, GNS was the first one. This came after that. So this was introduced despite the availability of GNS. And the difference I mentioned when I mentioned about the backward compatible, right? That there is no need for your application to be strictly sequential. That's one of the difference. In case of GNS, you have to be sequential. When you write, you cannot overwrite. You have to write sequentially. And you would end up doing the garbage collection because you would write in a similar fashion how SSD does, basically. And the second part here is that, yeah, as I said, right, this is like more kind of tolerant. So in case of this, I think what happens is that in case of GNS, if your application was anyway log structured, if it was having, if it was writing anyway in a same fashion, I think you probably won't have to change much because your application and the GNS may be a good fit, right? And you can actually use that. But if it is not, if your application is different, right, and you want to do the incremental changes, right? So then, in that case, FDP is a better choice because you could improve things incrementally. So that's the core difference between the two. And I think also it's about where it is being deployed. So on enterprise class versus data center versus mobile. So I think things are varying. So what we see is that there is good traction for GNS in the mobile side, while on the enterprise side we see the opposite. I think you probably would have heard about maybe zoned UFS. I think Pixel 10 is going to have zoned UFS support. I think last week or something there was an announcement, right? So, yeah. But I think that kind of tells that people are trying to solve the problem. I mean, the main problem is about the placement, right, and the kind of implications that it has, and how to go about improving it. There's just two ways to go with their own benefits and trade-offs. Anything else? So thank you so much for attending.